Before we start to look at integration, we need to make sure that our differential calculus skills are up to scratch. So what I suggest you do is just have a go at these few questions and then follow through the answers if you're not quite sure what to do. First question is then fairly straightforward. So here we've just got a cubic to differentiate. So if you remember back to the power rule, you would have, to differentiate x cubed, you would have brought 3 down and multiplied by x to the power 3 minus 1. We've got a constant in front of it, so this is the constant multiple rule. So you'd have multiplied 4 by the derivative of this. Similarly, we've got another function here. So if we've got two functions which we're adding together, we're just going to be using the addition rule. So I've differentiated this function, therefore I'm also going to differentiate this function and add them together, and I've got a constant at the end here which I just differentiate to get 0. I can then simplify all that to give me 12x squared plus 4x. For part B, one of the tricks here is to recognise that the fifth root of x is in fact x to the power 1 over 5. Once you've done that, you can use the constant multiple rule to find the derivative of that, which gives you 3/5 x to the power negative 4 over 5. The negative power is a bit untidy to leave it like that. We tend to rearrange it, so the negative sign means this is 1 over x to the power 4/5. So if we've got 3/5 times, again constant multiple rule here, 3/5 times this is going to give you 3 over 5x to the power 4 over 5. We can leave it like that, or we can put it back into the same form that was given to us in the question. Part C then is just going to be a case of expanding the brackets to give you a quadratic, which you can then differentiate. Part D, you may be thinking quotient rule or product rule. Either of those would also give you the same answer, but perhaps the simplest form is to recognise that you've got a common denominator, so you can rewrite it like this and simplify, and then it's just a case of the constant multiple rule and the addition subtraction rule to end up with the answer of 8x plus 2 plus 3 over x squared. So question 2 then, looking at special cases. So here we're just remembering that, again, this is the constant multiple rule, but remembering the derivative of e to the x is in fact e to the x. And similarly here we're looking at the addition rule and remembering that the derivative of ln x is in fact 1 over x. Chain rule then, this is just a little bit trickier. So for this function f of x equals 4 times 5x cubed plus 2 to the power 6, we're going to designate ux as 4x to the power 6, and then we're going to designate v of x, this section inside the brackets, which is 5x cubed plus 2. So we then need to find the derivative of this function, which is just 6 times 4 is 24, x to the power 5, but we've actually got a v of x here is 5x cubed plus 2. So we substitute that back in, then we multiply that by the derivative of vx, which is 15x squared. And if you need to go with the chain rule, it might be worth having a look at the video on the chain rule again. That gives us an answer here then of 360x squared times 5x cubed plus 2 all to the power 5. Part B, again, it's just a case of recognizing that when we've got a root, we can express that as a power, and then just recognizing your two components, u of x is just going to be x to the power half, v of x therefore is going to be 4x squared plus 1, derivative of this is half x to the power negative half, and then we substitute back in here for v of x and multiply that by the derivative here of v of x. Part C, again, recognizing that we've got e to the x, and then we're designating v of x as x squared. So if we find the derivative of e to the x, that is in fact e to the x, but remember we substitute in for v of x here, which gives us x squared, and multiply by the derivative of v of x. Couple of quick questions on rates of change of motion in a line as well, just to get you back into the right way of thinking, because this is actually going to be a nice link into integration, which is where we're headed next. So again, just pause the video and have a quick look at these questions. First part then, in order to find the average acceleration, we don't actually need differential calculus at all. We're just going to find the change in velocity and divide it by the change in time. So we can find the speed. If we substitute in 4, we can find the velocity at 4 seconds, subtract the velocity at 1 second, and divide that by the change of time, which gives us negative 12 meters per second squared. Remembering that velocity is a scalar, a vector quantity, which is why you also have the direction here. Find the instantaneous acceleration of the particle at time t equals 3 seconds. Whenever we see instantaneous, we should be thinking differential calculus. So therefore here, the relationship between acceleration and velocity we can find here is that if we've got the acceleration, at, the derivative, acceleration is the derivative of velocity. So what that's saying is the rate of change of velocity is the acceleration. So we can find the derivative here, the rate of change of the velocity, which gives us 12t minus 42, so that is the acceleration, which means it is decreasing at 6 meters per second. Again, acceleration is a vector quantity. So let's have a look at how we can bridge the gap then with integration. So if we have a particle moving in a straight line with a displacement of s meters, t seconds after leaving a fixed point, the displacement function is given by this: 2t cubed minus 21t squared plus 60t plus 3. So the first thing to do then is just think about how we can find the velocity of the particle at any time t. So just try and have a go at that. So the velocity is the derivative of displacement. The rate of change of displacement with respect to time is the velocity. So we can just find the derivative s dash t, which gives us this. My question then is, can you find the displacement function for a moving object if you know the velocity function? So what we've done above here, I've given you the displacement function, you've found the derivative of it in order to find the velocity. So if I was to give you a velocity function, for instance this one here, 2t plus 1, can you work backwards to work out what the original displacement function would have been? So just try and have a go at that now. So we've got this question here. The task then is this: to find a function such that the derivative of the displacement gets you back to 2t plus 1. Now I suspect most of you probably ended up with this, which it is correct. If I find the derivative of this, I do get back to 2t plus 1. This is the process of integration. However, as we'll see in a minute, there's more than one solution here. This is not the only solution. But at this stage, let's just note that the process, what we've just done, kind of working backwards, is called integration. So if we're given a function and we want to find what's called an anti-derivative, so that when we differentiate this, we get back to the beginning, this whole process is called integration, and effectively it's the opposite of differentiation. So st, the displacement function, if we've been provided with the velocity function and we've had to work backwards to come up with the displacement, this is called the antiderivative. And we can check that we're correct, because if we take the derivative of this, it should end up back at 2t plus 1. But as I said to you, there will be other solutions. So just have a think now what other solutions there might be, and why or how many there might be. Well, if we have a look at this function here, 2x plus 3, the antiderivative could be x squared plus 3x. If we differentiate this, we get 2x plus 3. So that is correct, but it could also be x squared plus 3x plus 1, because when I take the derivative of this, I end up with 2x plus 3. Could also be this, x squared plus 3x minus 6, because when I take the derivative of this, I also end up with 2x plus 3. And indeed, there's an infinite number of answers that I could have here. So this constant value here could be anything at all, and when I find the derivative, I still end up with 2x plus 3. So in general, any form of the function, x squared plus 3x plus c, will give us the derivative of 2x plus 3. So this value here, c, we actually write in as c, and is an arbitrary constant. So what I want you to do now then is to try and derive a formula for a general formula for the antiderivative. So let me just talk you through this example here. Suppose I give you a function. So suppose the function you have is x. What I want you to think of is how we can integrate this, find an antiderivative. So find a function such that once it's been once you've found the derivative, you get back to this value here of x. So if I start with x, I know that the x is going to have to be x squared. The reason it's going to have to be x squared is when I differentiate x squared, I get 2x, and I want x. However, I only want x. If I differentiate x squared, I get 2x. So therefore, I need to introduce this term here, half, such that when I differentiate this, x squared, if I find the derivative, that's 2x times a half. Using the constant multiple rule, it's going to give me x, which is going to take me back here, because this disappears as a constant term when I find the derivative. So just try and have a go at completing the rest of this table, and indeed, ultimately, see if you can find an expression or a rule for the antiderivative of x to the power n, which would be the general formula. So x squared, if we want to end up with x squared, we know that the antiderivative is going to involve x cubed, because if I differentiate x cubed, I will get 3x squared. I don't actually want 3x squared, I only want x squared, so I'm going to have to multiply by a third. And again, add the constant. Similarly, x cubed, I know that it's going to have to involve x4, because if I differentiate x to the power 4, that will give me 4x to the power cubed. Again, I don't want 4x, so I'm dividing 3 by 4 here. And similarly, 4x to the power 4. Generally, then, you should have noticed this pattern. If I want to find the antiderivative of x to the n, it's going to be 1 over n plus 1, x to the power n plus 1. So if we just look at this last one here, x to the power 4, if I try to do it using this formula, it's going to be 1 over 4 plus 1, so 1 over 5, x times n plus 1, so x to the power 4 plus 1 gives me 5, plus c as well. Are there any values of n where your rule does not apply? Well, yes, there is going to be one where n equals -1, and the reason for that should be fairly transparent. If n is -1, -1 plus 1, it's going to be 0, which is going to render this as undefined. So just to finish off this introduction into integration in terms of finding the antiderivative, here are 3 questions for you to have a go at. So the first question then, using the general formula that we looked at on the previous slide, we want to find the antiderivative for x to the power 10, so it's going to be 1 over 10 plus 1 times x to the power 10 plus 1 plus c. Do not forget plus c, very common mistake. We can simplify that, and that's going to give us 1 over 11 x 11 plus c. Part B, again here, recognizing this is just x to the power -5, and then using the formula 1 over -5 plus 1, x to the power -5 plus 1 plus c, which gives us -1 over 4, x to the power -4 plus c. Finally, and again, sorry, here, if we've got a negative power, we can just tidy it up, writing it as a positive power. Same thing, just in terms of notation, slightly neater here. Part C then, finally, again, recognizing just the notation, 4/3 of x cubed we can write as x to the power of 3/4. if that's our function, we want to find the antiderivative, so it's going to be 1 over 3/4 plus 1 times x to the power 3/4 plus 1 plus c. 3/4 plus 1 is 7 over 4, times x to the power 7 over 4. 1 over 7 over 4 we can tidy up by flipping the denominator to give us 4 over 7 x to the power 7 over 4 plus c. So in this introductory session on integration, we have looked at how to find the antiderivative for specific cases, and more generally how we derive the general formula for the antiderivative.